Okay, so this is the paper you did today. Draw the Lewis structures of oxygen and ozone. Okay, so let's do that nicely. First of all, let me hide this down here and get a nice color. This is a nice color. So oxygen looks like this, doesn't it? O double bond O, and we've got to put the electrons on there to make 8 electrons around each one. Ozone is going to look like this. Okay, so we have to put 8 electrons around each oxygen. So there's 8 there, plus the 2 of the bonds. There's only 2 there, plus the 3 bonds, and it's going to be 4 here. Okay, now obviously ozone, because you have a double and a single bond, is going to exist in this kind of resonance structure. Okay, so obviously either of these is good. You're not supposed to do this at this stage. It's for the next part of the question, but while we're doing it, so ozone exists as a resonance structure. Okay, and if you were to see ozone, I don't know, if you'll ever see it, it would be something like this. It would be kind of like a bond and a half. Okay, so this bond is going to be the same as this bond. Ozone doesn't exist in this structure or this structure. It kind of exists in a mixture of the two. All right, it's kind of an average of the two. Okay, it doesn't really even resonate between the two. It's kind of these Lewis structures show sort of official Lewis structures. These things show where the electrons are, really, where electrons are. It's in a way of accounting for electrons. Accounting for electrons. Now, the actual shape is a bit more complex. It would be some sort of mixture of these two. All right, and this is often how we show it, like a bond and a half. So the next one, that we've already explained this. Outline one of the bond lengths. The bonds in ozone are the same length. Well, because it exists in a resonance structure. Okay, and the bond lengths are the same. The O and O, these bond lengths are the same because it kind of averages out. So the bond lengths are the same because of resonance. Bond lengths are the same because of this resonance structure. What is the bond length? Well, you have to go to the data booklet, and I've got one here. I think I've got one here anyway. I did have one here. Yeah, this is covalent bond lengths. Now, oxygen single bond, and OO has a bond length of 148 picometers, and an O double bond O has a bond length of 121 picometers. Don't forget, a picometer is 10 to the minus 12 meters. So this in ozone is going to be somewhere between these two. So a decent guess, I don't know, is 130. Let's say that. 130 picometers in ozone. All right, there you go. Predict the bond angle. Well, it's going to look something like this, isn't it? It's going to be like that. And as we say in chemistry, it has 3 electron domains. Okay, so the electron geometry is going to be planar, isn't it? It's going to be trigonal planar. Okay, which is kind of that shape, isn't it? Okay, but don't forget the molecular geometry is not going to be that, is it? It's going to have this one knocked off, so it's going to be V-shaped. It's a V-shaped molecule. And the bond angle, if it were trigonal planar, it would be 120. But because of the lone pair here, they push these bonds down a little bit. So it's going to be a little bit less than 120. So 119 is good. It's a good guess there. All right, so the bond angle in ozone is going to be about 119. All right. Okay, now I'm digging around here for the next question. All right, so let's increase that size, decrease this. I don't know why it does this. It pastes it really big. I'm trying to get it so it looks nice on the PDF when I send this to you. All right, discuss how different bond strengths between oxygen atoms in O2 and O3 in the ozone layer affect radiation reaching the Earth's surface. Okay, now this is just comparison of the oxygen and the ozone molecules here. So let's get a nice color. That's red, I think. So you've got an oxygen-oxygen bond here, and this is stronger bond. Okay, and in ozone, you've kind of got 1.5, haven't you? So we'll draw it like that. So this is a weaker bond. Okay, so the stronger bond of oxygen will absorb more energetic photons. Okay, and the weaker bond here will absorb less energetic photons. Okay, so let's quantify that a little bit with an equation. So E is equal to HF and E is equal to HF. So the photon they're going to absorb is going to have energy HF. Obviously, Planck's constant, the H, is the same. But the energy for the O2 molecule is going to have a frequency of F1, say, and for the ozone it's going to be F2. Now, because this one E1, E2, because the energy absorbed in oxygen is going to be greater, E1 is going to be greater than E2. Why is that? Because it's a stronger bond in oxygen and it's a weaker bond in ozone. So because of that, we can say the frequency is going to be greater in oxygen. So the oxygen is going to absorb photons of a higher frequency. Okay, I'm looking at the question. Yeah, so there you go. So oxygen is going, and you've got to say about the bond strengths, by the way, is going to absorb higher frequency radiation than ozone. All right, purely because its oxygen has a stronger bond. Now, obviously, the greater the frequency, the wavelength is going to be less, isn't it? So the wavelength absorbed by ozone, this is lambda 2 and lambda 1. In this case, because as the frequency increases, the wavelength decreases. So oxygen is going to absorb lower wavelengths than ozone. Okay, I think that's kind of makes sense. I hope it does anyway. Right, let's have a look at the next question. Identify, let me try and do this 2 chunky bits here. Okay, let's push this up. Paste it there. Make it 100. Identify which steps absorb ultraviolet light. Well, if you go to the top here, all right, now the steps that are going to absorb is going to be bond breaking. So this is going to be an absorption because we need to break the bond. This is bond making, so that's going to be an emission. This is breaking bond, so this is going to be absorption as well. And this is a bond making, so that's going to be an emission. So those steps 1 and 3 are going to be absorption. Simple as that. That's all they want now. Okay, so identify the steps in which ultraviolet is absorbed. That's step 1 and step 3. Determine, showing you work in the wavelength in meters of ultraviolet light absorbed by a single molecule in the steps using 1, 2, and 11 of the data booklet. All right, so using 1, page 1, we get energy equals HF, which we know already. Excuse me, this is from section 1. Section 2, we get what Planck's constant is. Now I'm guessing this a bit. I know it's roughly about this, minus 34. You can look up the units yourself. I can't remember the units. All right, and part 11 of the data booklet gives us the bond energy of an O2 molecule. So it's 498. So the bond energy, E of OO, is equal to 498 kilojoules per mole. All right, using that bit, we've got to give the wavelength of ultraviolet light by a single molecule. Wow. Okay, so energy absorbed is going to be 498,000 joules. All right. Now, that's for a mole. So let's give them one molecule. So divide that by Avogadro's number. 6.02 times 10 to the 23. And this is going to give me the energy required for 1 mole. Let me do this on my calculator. So it's 498,000 divided by 6.02 exponential 23. And I get 8.27 times 10 to the minus 19 joules. All right, so that's the energy for 1 photon. Now, rearranging this equation here, all right, we get frequency is equal to energy divided by Planck's constant. However, we don't want the frequency, we want the wavelength. So the wavelength is going to be the reciprocal of this. So it's going to be Planck's constant divided by the energy. Planck's constant is 6.63 times 10 to the minus 34 divided by 8.27 times 10 to the minus 19. And that's going to give me a wavelength in meters. I hope it is anyway. Right, here we go. Let me get rid of this. So this is 6.6, whoopsie daisy, 6.63 exponential minus 34 divided by 8.27 exponential minus 19. And I get a wavelength of 8 points. Let me squeeze this in somewhere. From this, I get 8.017 times 10 to the minus 16 meters as a wavelength. Okay, let me check the answer scheme, make sure I got it right. Right, did I? No, I didn't, apparently. I got it wrong. What did I do wrong there? Oh, I see. They've done that as well. Okay, so I got this right. Whoops, it is. Why is that gone a bit weird? I've got the 8.27, right? That's the energy. Okay. Oh, they've done it. Oh, that's weird the way they've done it. But never mind. They've done it like this. They've done. So I think I did something wrong in my conversion up here. Okay, so they've done C equals F lambda. All right, now we've got the number of joules. Okay, so let's find F from this equation here. It's the energy, which is 8.27 times 10 to the minus 19, divided by Planck's constant, 6.63 times 10 to the minus 34. Okay. All right. Where are we here? I know what I've done wrong, actually. It's a bit stupid what I've done. But never mind. Let me get the calculator out. So it's 8.27 exponential minus 19 divided by 6.63 exponential minus 34. So the frequency, why doesn't it give it in standard form? So the frequency is 1.247. Why on earth hasn't done this? So that is 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15 times 10 to the 15 hertz. All right, that's the frequency. And now what I just did the inverse of the frequency to give the wavelength. So I did this, okay? But I shouldn't have done this. I should have used the speed of light. I should have done like this. If that. All right, so therefore the lambda, what we need, the wavelength, is the speed of light, 3 times 10 to the 8, divided by 1.247 times 10 to the 15. Hopefully, This will give us the answer. Okay, which is 3 exponential 8 divided by 1.247 exponential 15, and I get 2.4 times 10 to the minus 7 meters. Okay, let's check the answers. And that's right, eventually. So, it's not a hard question. I just rushed through it, didn't I? So you need this one. All right. You also need speed of light is equal to f times the lambda. All right, which I didn't use. All I did was I just used the inverse of the frequency to give me the wavelength. All right. So basically what I did is an old physics trick of counting the speed of light as 1. And so f is equal to 1 over lambda, which I shouldn't have done. All right. So there you go. So you get lambda equals 2.4 times 10 to the minus 7. That was, how many marks is that? That's only 2 marks. It's quite a lot of work for 2 marks there. All right. I hope you understand it. If you don't, give me a shout and I'll redo it for you. Okay. Now let me stop the video for a second. Okay. And have a look at the next bit. Okay. So this one's about nitrogen monoxide. And its catalytic effect of the ozone layer. Ozone depletion is catalyzed by NO, which is produced by aircraft and motor vehicle engines, as the follows loose structure. Show how nitrogen monoxide catalyzes the decomposition of ozone, including equations in your answers. Now, well, you've got to know this, I'm afraid, guys. So nitrogen monoxide is a free radical. These represent lone pairs, by the way, these lines. All right, that is a free radical. This is an unpaired electron. All right, and that means it's a free radical. So we can write it like this. That's going to react with ozone. It's going to grab the oxygen from the ozone and leave an O2. So we've smashed up the ozone and made it into NO2 radical. It's still a radical. This is a propagation step, if you remember. All right, where a free radical gives a free radical. And now this guy here, NO2, is going to react with another ozone. It's going to regenerate my catalyst NO plus 2O2. All right, so these have just got to be learned, I'm afraid. Learn this. Okay. The nice thing here, if you like, is, let me get a nice color for this, is the regeneration. So NO is regenerated. That's catalytic behavior. And if you like, if you started at this one, the NO2 is also regenerated. So that's part of the catalytic system. So the catalytic system in this case is NO and NO2. It's not one or the other, it's both. Both are part of the catalytic system because they're both regenerated. All right. Now let's have a look at the next one. All right, that was quite hard, actually. Ozone is a very particular one. Nothing to say about that, but just learn your ozone chemistry. All right, simple as that. All right, let me pause the video. Here we go. This is oxygen demand, biological oxygen demand. It's on the course, so we should know it. And it's often given the abbreviation BOD. Okay, biological oxygen demand. First of all, we've got to find the mole ratio of S2O3 to O2. Where's my pen? So there, where we started. We're going to start here. Okay, 2 of those. All right, reacts with 1 of those. So we've got 2 there, and there's a 1 there. There's a 1 there, and then there's a 1 there, and then there's a 2 there, and there's a 1 there. So what's the ratio? Okay, let's go. Right, for 1 oxygen here, we get 2 of those. So 1 goes to 2, and then 1 goes to 1. So 2 is going to go to 2. And then the last step, 1 goes to 2. So this is 1 and 1. So if I've got 2 of those, it's going to give me times 2, 4 of those. So I hope you understand how I did that. Just working carefully through the reaction. So we got for every S2O32 minus in ratio with the O2 it's 4 of these to 1 of these. All right, it's trickier than it looks, this one. So let me do it again. We started off with 2 of these. That reacts with 1 of these. Okay, so there's 1 of these, and it reacts with 1 of these. So therefore, 2 of these will react with 1 of these. And then 2 of these react with 1 of those. So in other words, 1 of these reacts with 2 S2O3s, but we've got 2 of them, so it's going to react with 4 of those. Okay, there you go, something like that. Anyway, I hope that makes sense. That's quite confusing, that one. All right, I think I've messed it up for you there again. Let me do that again because I don't feel confident that I've explained that nicely at all. So let's start again. All right, so let's say we've got to go from oxygen to sulfur, this guy, the thiosulfate ion. So let's go from the top. 1 of these gives me 2 of these. Okay, 1 of these gives me 1 of these, but I'm given 2 from this one, so 2 of those is going to give me 2 of those. Therefore, in this one, I'm going to get 2 of those, 2, and therefore I use 4 of those. So it's going to be a 4-to-1 ratio. It's a lot of work for 1 mark, I must admit, and it's easy to get wrong, trust me. All right, so let's have a look at the next bit. I think this was asked for by all of you. This video is getting long, isn't it? Way too long. All right, I didn't want it this long, but never mind. I hope you read it or watch it or whatever. All right, calculate the number of moles of oxygens in the day 0 sample. So here we go. Now let's go up to this. All right, so we're going to have to do some calculations here. Nice pen. Let me use that color. All right, so where are we? We use that thiosulfate. Okay, so calculate the number of oxygens in the day 0 sample. So that's the titer, and we're titering it with that. So the number of moles of S2O3 2 minus is equal to 0.1 times 25 times 10 to the minus 3, which is using that, which is 2.58 times 10 to the minus 4 moles of that. Okay, so that's the number of moles of thiosulfate. So therefore, the number of moles of oxygen from what we've just done is this number divided by 4. Whoopsie daisy. Let me move that up. Okay, divided by 4. Okay, because we had a 4-to-1 ratio. Now, the good thing is there is even if you didn't know it, they tell you. Oh, no, they don't tell you, do they? I thought they gave you the ratio. But the ratio is 4-to-1, and using that, you get the number of moles of oxygen is 6.45 times 10 to the minus 5 moles of oxygen. Okay, so it's pretty tricky if you didn't get this one. All right, so there you go. The day 5 sample contained 5.03 times 10 to the minus 5, I think that says, moles of oxygen. Determine the 5-day biochemical oxygen demand on the pond in milligrams per decimeter cubed, parts per million. All right, so now difference in moles. The difference in moles per dm cubed is equal to 6.45 times 10 to the minus 5 minus 5.03 times 10 to the minus 5. In other words, the difference between these two. Okay, we've worked this one out and it's given us this one. So this is the number of moles of oxygen in day 1. This is the number of moles of oxygen in day 5. So obviously it's that minus that. Okay, so that's the difference in moles, is that. Okay, let me work that out so I can put it down nicely. Calculator. Right, it's 6.45 exponential 5 minus 5.03 exponential minus 5 again. And we get that 1, 2, 3, 4, 5. we get a difference of 1.42 times 10 to the minus 5 moles. Okay, there you go, that's that. And now what I've got to do is to ratio that number up, because this is for 300 centimeters cubed. So to ratio up that to a decimeters cubed, we times it by 3 1/3, don't we? So in 1 decimeter cubed, the difference would be 1.2 times 10 to the minus 5 times 1,000 divided by 300. That's 3 1/3, isn't it? Okay, so that's ratioing it up. Let me get my calculator. Here we go. And that gives me 1.42 exponential minus 5 divided by, times 1,000 divided by 300. And that's that. So I get 4.73 times 10 to the minus 5 moles per decimeter cubed. Now I'm going to convert that to grams per decimeter cubed. So I'm going to times 4.73 times 10 to the minus 5 times 32. All right, that's grams. Now that's changing it to grams per decimeters cubed because the relative molecular mass of oxygen is 32. So times that by 32, and I get a very small number, 0.001515 grams per decimeter cubed. And now I times that by 1,000. Okay, and I get milligrams. So 1.515 milligrams per decimeter cubed. Hope that makes sense. It's a bit of a long-winded way of doing it, but there you go. So first of all, we found out the difference in oxygen between day 1 and day 5. But that was only in 300 cc's. So we had to ratio that up to 1,000, and then we get this answer. We had to change moles per decimeter cubed into grams per decimeter cubed, and we do that by timesing by the relative molecular mass. And then we get grams per decimeter cubed, then we times that by 1,000 to get milligrams per decimeter cubed, and we get that answer. Hope that makes sense at all. All right. Calculate the percentage uncertainty of the day 5 titer. Well, it's going to be, let's have a look at the titer itself. It's 20.1, isn't it? All right. So now a titer has an error of 0.05, but we go there twice, don't we? We find an initial and a final. There you go. Divide that by the 20.1 and times this all by 100%, and this gives us an error of 0.5%. Okay, learn how to do those. They're pretty straightforward. Suggest a modification to the procedure that would make the results more reliable. To make more reliable results, we repetition, and average. Okay, that's always a good, steady way of doing it. All right, let me pause the video there for a second. A nice bit of organic for us now. This is quite straightforward, isn't it? So propane is, let's have a look. Propane does something or other. We'll see in a minute. Propane is an important starting material for many products. The following shows some compounds which can be made from propane. There you go. State the type of reaction there. Well, to convert it to that, we've added HCl, so it's going to be an addition reaction, isn't it? That's good enough, but I'd rather you say the proper mechanism. It's an electrophilic addition. State the major product. And now propane looks like this. Oh, gosh. All right, my recording is going to stop in 20 seconds. So